Okay. So in my previous class, I have taught you about minimization problem in linear programming. That means how to solve the minimization problem in linear programming. Today I will tell you how to solve the dual simplex problem in linear programming. That was maximization problem was also a simplex type of problem. Minimization problem was also a simplex problem. Here dual simplex means it involves the constants having both the symbols greater than equal to, less than equal to or maybe equal to. So let me write down one problem for that. I have noted down all the steps. First, let me write down the problem. Then you can see what kind of problem is that. Let's say this is one problem. Solve the LPP linear programming problem by dual simplex method. This is the question given to you. Here it is given maximize z objective function and it is minus 3x1 minus 2x2. Subjected to the constraints are x1 plus x2 greater than equal to 1.
Excuse me, ma'am. Ma'am, your screen isn't visible.
Okay. Just wait. Okay. Now I have shared it. Is it visible now? I think now you can see the screen. Shashwat, can you see
Yes,
the
ma'am.
screen? Okay.
Yes, ma'am.
Okay. Let's start.
Yes, ma'am.
Okay. So this is a dual simplex problem that I am going to solve in this class. You see in this problem it is written that solve LPP by dual simplex method. It is maximize z is equal to minus 3x1 minus 2x2 such that your constants are x1 plus x2 is greater than equal to 1. Next is x1 plus x2 is less than equal to 7. Then x1 plus 2x2 is greater than equal to 10. Then x2 is greater than equal less than equal to 3. These are the four constraints given to you, and it is given that all both x1 and x2 are greater than equal to 0. These are the constants given to you. And in the previous class that I have taught you that for maximization problem, this is the problem of maximization. For maximization problem, all the constant symbols should be less than equal to. But in this case, in this problem, you can see that you are getting the mixture of greater than equal to, less than equal to for all these constants. This shows that this is a dual simplex problem. So you have to solve the dual simplex problem. You have to solve this problem by dual simplex method. Now, how to solve the dual simplex method? Dual simplex means it involves both it involves greater than equal to, less than equal to, maybe equal to symbol also in the constraints. So very first step that you should follow is that convert the problem into a maximization one if it is a minimization one. And how you will multiply it? You will multiply it by multiplying minus 1 to it. So you can see that here this problem is already a maximization problem. So in this case it is no need to convert this into a to maximization 1. If instead of maximization z it would have been it would have been minimization 1. दे दियो दोबारा से शुरू कर देती दोबारा Okay, so This one you can see. So this is, now you can see that this problem, if it is already written, it is a maximization one. So for maximization one, this rule number one, no need to follow for this problem. This problem is already in a maximization mode, so no need to multiply it to -1. If it would have been minimized z minus 3x1 minus 2x2, then you would have multiplied it the both the side. You would have multiplied it by -1. Then it would have been minimized z. It would have been maximized z 3x1 plus 2x2. But no need to go into that. I'll work out that kind of problem also. So first rule is that convert the problem into a maximization one. Second, if there are any greater than equal to type constant, convert it into a less than or equal to type of constant by multiplying both sides by -1. Because for maximization problem, we always need a less than equal to type of constant. So it can only be done if you multiply both sides by -1. Then as usual process, you have to compute Cj minus Zj for each column. And if you see that all Cj minus Zj are negative or zero or contribution quantity is positive, then that is your optimal feasible solution. What happens usually that in your maximization problem as well as minimization problem, your contribution quantity, that means these will be the contribution quantities. These. So these contribution quantities are all are positive. But in case of dual simplex problem, if you see, if I convert this one, this greater than equal to symbol, you will multiply -1 here, your contribution quantity will be -1. So in this case, there are chances that the contribution quantity may be negative. So if all the Cj minus Zj are positive, are negative and 0, and all the contribution quantities are positive, that is the optimal feasible solution. So and if all the Cj minus Zj are negative and 0, but one or more contribution quantity are negative, means you have to work out and go to the next step. Then you have to choose the most negative one of the contribution quantity. That will be the key row. In your maximization and minimization problem, first of all, we used to select the key column. Then after that, we used to determine the key row. But in case of dual simplex problem, first we will choose the key row. Then after that, we will determine the key column. Then if any Cj minus j are negative, are positive, then if third condition is that if you compute Cj minus Zj and all are positive, then this method cannot be applied. So you need all the Cj. For if you want to use this method, Cj minus Zj should be either all negative or 0. Then how to use choose the select row, key row. Select the row that contains the most negative value, that is a negative value, that is your key row. Then you have to determine if all the elements are non-negative, the problem does not have a feasible solution. If at least one element is negative, you have to determine the ratio of Cj minus Zj divided by corresponding element in key row. That when I'll work out the problem, you will see how I'm calculating this one. Then select the smallest positive value of these rows, that will be the key column. So first in this case you're determining the key row, then you're computing this calculation, and from that which one is the smallest positive one, that is your key column. Then where the key row and key column will intersect, that will be the intersection element. Then you will follow the rule as usual that we have worked out for maximization and minimization. So let me work out this problem. So this is in this problem is always already in maximization mode. So no need to convert into maximization. But here the constraints, you can see that we have to now constraints x1 we will multiply -1 to both the sides, minus x1 minus x2, then it will be converted into less than equal to -1. So we need always less than equal to type of constant for maximization problem. Then second constant is okay, x1 plus x2 less than equal to 7. Then x1, then it is again it is greater than equal to, then minus x1 minus 2x2 less than equal to -10. Then x2 is okay, x2 less than equal to 3. Now we have converted all the constants in the form of less than equal to type. Now we will write the, now as usual process for maximization. For maximization problem, you have to remove this inequality and put it in equal symbol. And for that we used to add slack variables s1, s2, s3 and s4. So this equation, this inequation will become equation as minus x1 minus x2 plus s1, usual procedure that I have told you, is equal to minus 1. Then x2, x1 plus x2 plus s2 is equal to 7. Then minus x1 minus 2x2 plus s3 is equal to minus 10. Then x2 plus s4 is equal to 3. Now what will be the objective function z now? Z is equal to minus 3. Z you can see that Z is equal to minus 3x1 minus 2x2. So it is your minus 3x1 minus 2x2 plus 0s1 plus 0s2 plus 0s3 plus 0s4. So this is now objective function. You got it, everything now. Similar procedure, you'll make the tables and fill it out. So now we need 4 rows for S1, S2, S3 and S4. So this is your coefficient of the basic variables, and your basic variables are your S1, S2, S3 and S4, and its coefficients are obviously 0, 0, 0, 0. Coefficients of basic variables S1 to S4, 0. Then here it is your Cj. Cj is the coefficient of the variables in the objective function. In objective functions, your coefficients are minus 3, minus 2, 0, 0, 0, 0. And here you write down the basis. This is your S1, S2, S3, S4. And here X1, X2, we have up to S1, S2, S3, S4. X1, X2, S1, S2, S3, S4. And these are the coefficients of your objective variables in the objective function, that is your minus 3, minus 2, 0, 0, 0, 0. And next column is the contribution quantity. Contribution quantity. Here we don't have the column that minimum ratio that we used to have it in maximization and minimization problem. Now we'll fill everything else here. So for first equation, minus 1, minus 1, minus 1, 1. And you know that this is the identity or unit matrix. So first case will be, it is 1, all others are 0, 0, 0. Second case, it is 1 here, 1 here, 1 here, all zeros, 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 zeros. Now we will fill one by one for all. So here it is minus 1, minus 1. So here it is minus 1, minus 1. Next case it will be, it is 1, 1. Next minus 1, minus 2. Then then it is your 0, 1. So, and what are the contribution quantities? Contribution quantities are minus 1, 7, minus 10 and 3. So just fill it out here. Minus 1, 7, minus 10 3. Now, we will compute Zj as usual. This is Zj, then here Cj minus of Zj. Zj. Now if you compute, it will be all zeros. Zj for first row, it will be 0, 0 into minus 1 plus 0 into 1 plus 0 into minus 1 plus 0 into 0. So it is your 0. Then here it will be all zeros because all the things are zeros, means you will get 0. And Cj minus Zj, it will be minus 3. It will be your minus 3, minus 3, minus 2 and all zeros. Now we have to start which one is the key. Here in this problem we have to first choose the key row. Key is the one which one is the most negative contribution quantity. You can see that the most negative contribution quantity is your minus 10. This is written in the rules. Which one you will choose? You have to choose, select the row that contains the most negative value, that is the key row. So here you can see that minus 10 is the most negative value, so it is the key row. Key row, most negative value, most negative value. So this is the key row. Now what we will do next step is that we can see that all Cj minus Zj's are negative and 0, and all our rule says that all Cj minus Zj values should be negative or 0, or and if all the contribution quantity would have been our positive, then we would have stopped here. That would have been the current feasible solution. But here it is negative 1. That means that there is an option for again working out. Then what we will do now, we have to compute another row, Cj minus Zj, as all the Cj minus Zj values are negative and 0. If it would have been positive, means we cannot work. It shows if all the Cj minus Zj are positive, means we cannot apply this method. As all are negative and 0, we can use this dual simplex method. And now compute Cj minus Zj divided by corresponding element in key row, in key row divided by. So here for this row, you can see that for this column your corresponding element of key row is minus 1. So minus 3 divided by minus 1, minus 3 divided by minus 1, it is your 3. Similarly for this row, it is minus 2 divided by this element minus 2, you get it is equal to 1. Likewise you will get 0, 0, 0, 0. Now after that we have to choose the smallest of all the positive values. These are the zeros. Zeros we cannot choose. Out of 1 and 3 here in this case, which one is the smallest? 1 is the smallest, that is your key. That smallest value will be the key column. Key column. Choose the smallest value, smallest positive value, not 0. Smallest positive value as key column. Now find out the intersection element of key row. This is key row and this is key column. So this is the intersection element, and here which one will be the outgoing variable and which will be the incoming variable. You see x2 will be the incoming variable, that means and s3 will move out. X2 will enter the solution and S3 will move out. Likewise, same process we will follow now. So it shows that S3 is now replaced by X2. X2. So now following the similar rules, this is CJ, this is basis 1. The CJ's values will fix throughout the iteration. It will not change. That means the coefficient of variables in the objective function. X2 here, S1, S2, S3, S4. Last is the contribution quantity. So here it is your -3, -2, here 0, 0. Till now I have not done anything. So first we will fill for x2, s3 because it will be replaced by, so here another column I needed when we have s4 variables. So here it will be S3 will be replaced by X2, and what is the coefficient of X2 here? It is your -2, so it will be 0 is replaced by -2 here, so it is your -2. All other remains same. It is 0, 0 S1, 0 S2 and 0 S4. Now what we will do? Now we will do the entire this row, this S3, this row divided by -2. That means -1 by -2, -2 by -2, then 0 by -2, 0 by -2, then 1 by -2, then 0 by -2, likewise -10 by -2. All if we first we will start from this row. So it will be 1 by 2 as usual process. 1, 0, 0, 0, again 1 by 2. So it is it is 1 by 2, 1, 0, 0, minus 1 by 2, 0, then here it is 5. And likewise you will, for maximization, how you used to fill the other row, same process you will repeat and fill it up as I have told you for maximization as well as minimization. So it will be -half, 0, 1, 0, -1 by 2, 0, 4. So I'm not repeating it every time. So it is 1 by 2, 0, you will get 0, 1, 1 by 2, 0, 2. Okay, you got it?
Yes.
Okay. Then S4. Then S4. S4 it is S4 S4 now it will be your minus half, minus half, 0, 0, then it is 0, 1 by 2, 1, minus 2. So, so you got it like this. So just now we have filled it. You have filled it. Then out of this, then what you will do, same process, you will compute ZJ and ah, now I think you can see. Next I'll come. Next similarly we will go for ZJ calculations and CJ minus ZJ as usual in the previous step. हाँ. Could you see this? नहीं, वीडियो कॉल एंड है, देख तुम बोले हो जाएगा. I think now you can see the screen, all of you.
Audio.
Could you hear me all?
Yes.
Could you see the screen? You cannot see the screen. Okay, let me share it again. Now could you see it?
Yes.
Okay, I'll continue. Okay, so now you will compute as usual process of ZJ and ZJ minus CJ minus ZJ. So here first of all you will determine the key row, most negative one, that is your minus 2. So this is your key row. So now you got the key row as it is the most negative one. Then this is your key row. Now you have to search for key column. For key column, you will first compute ZJ. As usual in the previous step, like you will get minus 1, minus 2, then 0, 0, 1, 0. Then you compute CJ minus of ZJ. You will get minus 2, 0, 0, 0, minus 1, 0. Then CJ minus ZJ. You can see that all the Cj minus J rule says that a Cj minus Zj should not be positive. So Cj minus, if it is positive means you cannot apply this process. As Cj minus Zj are 0 and negative, so you can follow this dual simplex method. and one of the contribution quantity is still now it is negative. So till now we have not reached the optimal solution. When you have the contribution quantity positive and all the Cj minus Zj negative and 0, then that is the optimal solution. So you will compute Cj minus Zj by corresponding element of key row, corresponding as you have done for the previous step, element of key row. So here it will be minus 2 divided by minus 1 by 2. So you will get 4. Similarly, you will get 0, 0, 0, minus 2 and 0. So which one is the key column? Which is the smallest positive value? So smallest positive value, there is only one positive value, that is your 4. So it is your key column. Key column is the smallest positive value. Then it is which one is the intersection element of key row, key column and key row? So this one is the intersection element. So it belongs to, so it shows that S4 will go out. S4 will go out and X1 will enter the matrix. So now next step is that you will just replace. So here row S4 will be replaced by X1. So 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 now first is that x1 s4 is replaced by x1 and its coefficient is minus 3. If you see in the matrix or here you can see its coefficient is minus 3. So 0 is replaced by minus 3 and it was your x2 and its usual minus 2, you can see here x2 minus 2, then these two will be same. So here it was your S1 0, S2 0. Now if you do all sort of calculations, so first you will compute for S4 row, that means minus 1 by 2 divided by minus 1 by 2, 0 by minus 1 by 2, all zeros, 1 by 2 divided by minus 1 by 2 and 1 divided by minus 1 by 2. So this row first you will compute it, that means this last row. So here you will get 1, this is 1, 0, 0, 0, then minus 1, minus 2. Similarly, all other rows you will fill using the process of maximization and minimization as I have told you. 0, 0, 1, 0, 1, minus 1, here it is 6, here it will be your 4. Similarly, here you will get 0, 0, 0, 1, 1, 1, 0, then 0, 1, 0, 0, 0, 1 and 3 as usual process if you follow. But you see that here you can see that here this last column is your contribution quantity. I've told you in the rules that when your contribution quantity is all positive, that is your case solution. So no need to go for further iteration as the contribution quantity has no negative value, as this column has no negative Negative, all are positive values, no negative values. So this is the key solution. Your x1 is equal to, so x1 is equal to your minus 3 and x2 is equal to your minus 2. So this is the this is your x1 and these two are the values. If you put it in your z main equation, what was the question? Maximize z is equal to minus 3x1 and minus 2x2. So z is equal to, finally your z max will be minus 3x1 minus 2, it was your minus 2x2. Now if you put the values, you will get minus 3 into minus 3 minus of 2 into minus 2. So what you will get, 9 plus 4, it is your 13. So this is the answer for Z max. So this is the way how you will solve the dual simplex problem. So let me summarize how you will solve the dual simplex problem. The first step is that, first of all, you will see whether the problem given to you by the dual simplex method is of maximization type or minimization type. If it is of minimization type, convert the problem to maximization one by multiplying minus 1 to it and minus 1 to it, and you can write down, if you multiply minus 1 to it, then you have to give at least z dash. I'll tell you one example by that. And then you have to, second, you have to check the constant sign, whether it is less than equal to or greater than equal to, or if it should be all less than equal to type of constant. If greater than equal to type of constants are there, you multiply minus 1 to both the sides and convert it into less than equal to type of constant. Then you will go for the substitution of all the variables and coefficients in the matrix, and you formulate x1 is your 4. You see, x1 is equal to your 4, this 4, and your x2 is your 3. So this is the equation. So after that, if you compute, you put the values of minus 3 x1. x1 is your 4 and your x2 value is your 3. So you will get minus 12 minus of 6. So it is your minus 18. So this is the solution of Z-max. So this was one of the way you can work it out. So another problem example I am giving you of dual simplex one, of it is of minimization time. Suppose it is given that solve the dual simplex method, minimize z is equal to 2x1 plus 2x2 plus 4x3, subject to 2x1 plus 3x2 plus 5x3, it is greater than equal to 2, then it is your 3x1 plus x2 plus 7x3 less than equal to 3, and x1 plus 4x2 plus 6x3 less than equal to 5. So this is the question given to you where x1, x2 and x3 are greater than equal to 0. So in the previous one, I have worked out for your maximization one. So now for this, I have told you that if it is a minimization one, we should convert it into maximization 1. So now you will multiply by minus 1, so it will be maximize. If you are multiplying it, you are changing it, means that then it will not be z. Let's say it is now z dash. Your objective function variable is your z dash, so it will be multiply minus 1 minus 2x1 minus 2x2 minus 4x3. Okay, then subject your constants, and you're converting it into maximization one, and you have to check your variables are of less than equal to type or not. You can see that only the first in equation is of greater than equal to type, so we have to convert this one into less than equal to by multiplying both sides by minus 1. So subjected to Your constants are minus 2x1, minus 3x2, minus 5x3 less than equal to minus 2. All and both you can just note it down under it. 3x1 plus x2 plus 7x3 less than equal to 3. X1 plus 4x2 plus 6x3 less than equal to 5. And now we have framed that thing. Now I think now this we have converted into a maximization type. Next similar process you will follow and work out this problem. So this completes your dual simplex method. Again, another thing I would like to tell you about the duality. So for that, how to determine the duality? Okay. And another example, let me show you that this is one example. And in another case, if you have only equal to symbol in this problem, you have greater than equal to as well as less than equal to symbol. If you are having only equal to symbol, then how you will work out whether it is a maximization one or whether it is a minimization one or it is a dual simplex problem. So let's say this problem is, suppose let's say problem 3. These problems you can work out by yourself and find out the solution. So I have just put it in pattern. So let's say there is one problem, maximize z is equal to 2x1 plus 4x2 minus 3x3, subject to x1 plus x2 plus x3 is equal to 8, then x1 minus x2 is greater than equal to 1, and 3x1 plus 4x2 plus x3 less than equal to 40. We are acquainted with our greater than equal to as well as less than equal to symbol. So now we will convert this into, if there is a equal to, so remember that if there is a equal to symbol, you will only add artificial variable to it. So it will be your x1 plus x2 plus x3 plus a1 is equal to 8, even though it is, because I have already told you that artificial variable has no significance, it has no value, so we add artificial variable to it. And it next equation is greater than equal to, means we will so if you remove this inequality, you know already x, either you can multiply minus 1 to it, or do it likewise, or or you can do x1 minus x2 minus s1 plus a2 is equal to 1. Likewise also you can do it, and this remains as it is, 3x1 plus 4x2 plus x3 less than equal to 40 as usual. Sorry, it is we want to remove it, plus s2 plus s2 is equal to 40. So now objective function will be maximize z is equal to, it was your 2x1 plus 4x2 minus 3x3. So now it is, we have S1, 2 S1, S2s are there, 0 S1 plus 0 S2. You know that when in objective function we used to give negative coefficient for M for A1, A2. So it will be minus M A1 and A2 is there, again A2 is there, so it is minus M A2. This is the format. So now as usual you can work out as a usual way. So it is the way you can work out. Now next last part of this chapter is your formulation of the dual formulation of the dual of the primal problem. So problem given to you is under this heading, minimize z is equal to 3x1 minus 6x2 plus 4x3. Subject to your constraints are 4x1 plus 3x2 plus 6x3 greater than equal to 9, x1 plus 2x2 plus 2x2 plus 3x3 greater than equal to 6, 6x1 minus 2x2 minus 2x3 less than equal to 10, then your x1 minus 2x2 2x2 plus 6x3 plus 6x3 greater than equal to 4, then your 2x1 plus 5x2 minus 3x3 greater than equal to 6. This is a question given to you. You have to find out the dual of the following LPP. So, solution. So, as it is a problem of minimization problem means all the symbols should be greater than equal to. So here this is less than equal to, so we have to only convert this into greater than equal to by multiplying minus 1 to it. So if we convert this you will get minus 6x1 plus 2x2 plus 2x3 greater than equal to minus 10. So now we have to find out the dual of this. So it will be maximize dual, maximize. Now your z will be your z dash, because it will be a different equation. So what will be, so it will be 9 y1 in this. When we make the dual means now our variables are y's instead of x. So 9 y1 plus 6y2, and here this equation has been shifted to this. It will be minus 10 y3 plus 4 y4 plus 6 y5. Subject to this is the new objective function of this dual of this problem. And what are the constraints now? Subject to constraints are your 4. These are this will be the first inequation, this will be the second inequation. That means this one is replaced by this one, and this will be the third inequation. So now it will be your 4, it will be your 4 y1 4y1 plus y2. You can see that this is 4y1 plus y2. This 6 has been replaced with minus 6y3 minus 6y3 plus y4 plus 2y5 plus y4 and 2y5. It is now, it is the maximization one. It is less than equal to your 3. And how, where is this 3? This is this 3. This is the first inequation. Then second inequation will be 3y1 plus 2y2 plus 2y3 minus 2y4 plus 5y5 less than equal to your minus 6. Likewise, three inequations you will get it. Now it will be your 3y1 plus 2y2 plus 2y3 minus 2y4 plus 5y5 less than equal to minus 6. Third will be your 6y1 plus 3y2 plus 2y3 plus 6y4 minus 3y5 less than equal to 4, where y1, y2, y3, y4 and y5 are greater than equal to 0. See, only the difference is your variables are, instead of x1, x2, x3, x4 and x5, it is your y. Now solve by usual process as I have told you. For working out the maximization problem, you will get the values of y1 and y2. So this completes your fourth module